You ever get tired of scientific explanations that feel, well, a little bit like magic tricks? You know, the Big Bang coming from a point that's infinitely small? Or particles that follow these strange rules we can't really see or feel? It's time we pulled back the curtain. What if the universe isn't some box of magic at all, but a powerful, predictable engine? In this explainer, we're going to take a look at its blueprint.
And that brings us to the big question, right? Is the universe built on abstract math and weird, counterintuitive ideas? Or is it built on solid, understandable mechanics? You know, are the laws that govern a bridge or a car engine the same exact ones that govern the entire cosmos? We're going to push the universe to its absolute limits and see what happens when it's forced to break.
And when you look, modern science is just full of these weird puzzles. The Big Bang, for instance, which seems to come out of a mathematical glitch. Or water, the very stuff of life that seems to defy thermodynamics by expanding when it freezes. You even have atoms, like chromium, that just kind of play by their own rules. Now, to an engineer, these aren't just quirks, they're clues to a much deeper mechanical truth.
To crack these cosmic codes, let's start with something really simple, a rubber band. You pull on it, it stretches, and it absorbs that energy. Believe it or not, this simple act of stretching and storing energy might just be the key to understanding how the entire universe works.
So as you keep stretching that rubber band, the energy from your pull doesn't just disappear into thin air. No, it gets stored as potential energy. It's the silent, invisible tension that's building up inside the band's structure. And the more you pull, the more of that tension you build.
But here's the thing. Everything has a breaking point. Eventually, that rubber band reaches its absolute limit. The outward pull from your hands is perfectly balanced by the band's own internal strength. It can't go any further. This isn't just some number on a page. It's a real physical wall. And this is the moment where the laws of mechanics are about to take over. So what happens when all that stored tension has absolutely nowhere else to go? It snaps. It's this violent, purely mechanical recoil. The system is forced to reconfigure itself just to release all that stored up energy and find a new stable balance. You could say it breaks in order to survive.
Now, this snapping back isn't just some random thing. It actually has a name, the Vidyabhushan-Bounce. That breaking point is called the Vidyabhushan point, and the snap itself is the bounce. This simple mechanical law, well, this is our skeleton key, and it's about to unlock some of the biggest puzzles in all of science.
All right, let's put this key to the test. We're going to start small, with the micro-engine of our world, and see how this mechanical blueprint can solve some of nature's most confusing little quirks.
Okay, let's take water. We're always told that the reason it expands when it freezes is just a weird anomaly of hydrogen bonds. But the V-Bounce model gives us a clear mechanical reason. As the cold compresses the water molecules, they get pushed closer and closer together until they hit their Vidyabhushan point. They literally can't get any closer. So what do? They snap into a whole new formation, this beautiful hexagonal lattice that actually creates more space. Ice floats not because it's quirky, but as a life-saving mechanical defense against being crushed.
And this same principle applies all the way down at the atomic level. Take chromium, for example. It always looks like it's breaking the rules of how electrons are supposed to fill their shells. But the V-Bounce model shows us it's just trying to balance itself. An imbalanced load creates internal strain. Think of a wobbly washing machine. So the atom snaps into a more symmetrical shape, moving an electron to achieve perfect stability. It's not breaking the rules, it's protecting itself from tearing itself apart.
Now let's look at really heavy atoms, like lead. There's this thing called the inert pair effect, which is usually explained away with some really complex relativity. But a mechanical view shows us something much, much simpler. The nucleus is so massive that it creates this immense inward pressure, and the atom is in a constant fight to hold itself together. Those so-called inert electrons, they aren't lazy. They're in a mechanical lockdown, pinned in place to brace the core against total collapse. The atom literally gives up its ability to bond with other things just to ensure its own survival.
Okay, so the V-Bounce model seems to work for the small stuff, but what happens when we apply it to the biggest machine of all? What about the universe itself?
Let's tackle relativity. The standard view says that as you get closer to the speed of light, your mass becomes infinite. But think about it. How can you create infinite mass just from motion? The V-Bounce model suggests something different. Imagine space isn't empty, but a physical medium, like a universal lattice. The speed of light is just the fastest this lattice can vibrate.
So as you try to move through it, you create drag. That relativistic mass isn't new matter at all. It's total impedance. It's the physical resistance of the fabric of space itself.
And now, for the biggest puzzle of them all, the Big Bang. With our mechanical blueprint, the Big Bang is no longer some magical random explosion that came from nothing. It becomes the predictable, mechanical recoil of a system that's at its absolute breaking point. It wasn't an explosion in space, it was an explosion of space.
The process is exactly the same as our simple rubber band. You had a pre-universe that was squeezed and compressed to its absolute limit until it hit the universal Vidyabhushan point. To avoid complete and total collapse, it had no choice but to snap back in a catastrophic recoil, the cosmic snap. And this expanding universe we all live in, it's simply that system settling down, finding a new, stable state of balance.
So, what's the big takeaway from all of this? Well, when we swap out the magic for mechanics, we get a whole new blueprint for reality, one that's built on stability and structure, not on randomness and chance. What this paints is a picture not of a universe filled with chaos and quantum quirks, but a universe of structural integrity. A giant, self-correcting engine where everything from a single atom to an entire galaxy is following one simple rule: survive, find balance, and when you're pushed to the absolute limit, snap back even stronger. And that leaves us with a pretty profound question, doesn't it? If the Big Bang wasn't just a random accident, but the first beat of a massive cosmic engine, then what does that make us? Are we just random noise in the system, or are we part of the symphony? Maybe, just maybe, our existence isn't an accident at all, but a fundamental frequency of the universe itself.